Have you ever stopped and wondered how we can possibly know what a distant star is made of, or figure out what's in a single drop of liquid without even touching it? Well, it's not magic. It's actually a secret language, one spoken between light and molecules. And today, we're going to learn how to read that language to uncover some pretty amazing secrets. It all comes down to what you could call a molecule's light fingerprint. See, every single molecule absorbs a totally unique pattern of colors, and by analyzing that pattern, we can identify it. But here's where it gets really cool. That fingerprint isn't always the same. It can shift and change, and when it does, it tells us a much deeper story. So the key to all of this is a tool called the absorption spectrum. Don't let the name scare you. It's just a graph, but think of it as our treasure map. It shows us exactly which colors a molecule soaks up and just how much of that color it's absorbing. This one simple graph is going to unlock everything for us.
All right, first things first, let's focus on the horizontal part of our map, the x-axis. This is all about shifts in color, specifically shifts toward either red or blue.
So that horizontal line represents wavelength, which our eyes just see as color. The easiest way to picture it is as a rainbow, right? You've got the shorter wavelengths like blue over on the left and the longer ones like red over on the right. So when we talk about a shift here, we're talking about a literal change in the color of light that the molecule is most interested in.
Okay, our first big term is the bathochromic shift. It sounds super technical, I know, but pretty much everyone just calls it a red shift, which makes it way easier to remember. This just means a molecule has started absorbing light at a longer wavelength, maybe because its structure changed a little bit, or something in its environment is different.
And on our graph, a red shift is super easy to spot. The main peak of absorption just slides to the right. It moves towards the longer, redder end of the spectrum. Simple as that.
Now, if you can shift one way, you can probably shift the other, right? And that's exactly what a hypsochromic shift is. You'll more commonly hear it called the blue shift. This is what happens when a molecule starts absorbing light at a shorter wavelength instead.
And on our graph, you guessed it, a blue shift is just a movement to the left. That absorption peak slides over towards the shorter, higher energy colors like blue and violet. Okay, let's lock this in. When we're talking about color shifts, a bathochromic or red shift is a move to longer wavelengths. That's to the right on our graph. A hypsochromic or blue shift is a move to shorter wavelengths, a slide to the left. Got it? Awesome. So we've covered the side-to-side movement. Now let's look at the vertical axis. This part isn't about what color of light is absorbed, but how much of it is being absorbed. It's all about intensity.
Yeah, that vertical line measures absorption intensity. I think the best way to imagine this is like the volume knob on a radio. If the peak on the graph is high, it means the molecule is turning up the volume and absorbing a ton of light. If the peak is low, it's turning it down. So when that intensity goes up, we call it a hyperchromic shift. Just think, hyper means more. It just means the molecule is getting way better at absorbing light at that specific color, maybe because a change in its shape turned it into a better little antenna for that light. And on our graph, this one's obvious. The peak just gets taller. The volume is cranked up, which means there's a much more intense interaction with light happening. It's a visual sign that the molecule is literally grabbing more photons. Kind of cool, right? And the opposite of hyper, of course, is hypo. A hypochromic shift is when you get a decrease in that absorption intensity. For whatever reason, the molecule has just gotten a little worse at soaking up that specific color of light.
So on our graph, this just means the peak gets shorter, the volume gets turned down, telling us the absorption is weaker or less intense.
So to recap the up and down changes, hyperchromic means the peak gets taller, absorption increases. Hypochromic means the peak gets shorter, absorption decreases. It's really just a simple up or down change on our map.
All right, we've looked left and right, and we've looked up and down. Now let's put it all together to get the complete picture of how a molecule's light fingerprint can change.
And this table just lays it all out perfectly. There are really just 4 fundamental shifts we need to know. For wavelength or color, we've got bathochromic for red shifts and hypsochromic for blue shifts. And for intensity, we've got hyperchromic for going up and hypochromic for going down. These 4 terms give us a complete language to describe pretty much any change in how a molecule talks to light.
Okay, this is all fascinating stuff, but let's get to the big question. Why does any of this actually matter? How do these tiny little shifts on a graph actually affect us in the real world? Well, it turns out the applications are huge and incredibly important.
You know, this is the exact language scientists use to design sunscreens that better protect our skin. It's how they develop medical tools that can spot diseases early. It's how they check the purity of our food and medicine. They even use it to watch incredible biological processes like DNA making copies of itself as it's happening. These tiny, subtle shifts in light are signals that tell us a massive amount about the world around us.
So, we've just learned how to read the invisible language of light and molecules. It really makes you wonder, doesn't it? What other secret languages are out there all around us, shaping our world in ways we can't even see, just waiting for someone to come along and figure them out?